This is sample exam 7, problem number 35. A bin of 10 light bulbs contains 4 that are defective. If 3 bulbs are chosen without replacement from the bin, what is the probability that exactly K of the bulbs in the sample are defective? Problem number 35. This ends up being a hypergeometric. If you separate the 10 balls into the defective and non-defective and then sample without replacement, that's a classic hypergeometric setting. And the answer is follows. 4 choose K, 6 choose 3 minus K, 10 choose 3. Number 36. Let X, Y, and Z be independent random variables, each uniformly distributed on the interval 0 to 2. What is the number C for which the probability is 75% or 0.75 that at least one of X, Y, or Z will exceed C? Number 36. Here we want to find the number C that makes this probability 0.75, and that's the probability that X is greater than C, or Y is greater than C, or Z is greater than C. So the trick to this is you take 1 minus. So 1 minus the probability that they're all less than C. Well, since X, Y, and Z are independent, you can break them up into the product of those, and those are a random sample from the same distribution. So this is the same as that, which is equal to this. So it's the same as taking one of them cubed, and then one of them, this probability, which we'll do down here, is C over 2, and that's raised to the cube, the third. And again, we want it to equal 0.75, which implies that 1 minus this is equal to 3/4, which is 0.75, implies that C is equal to 2 raised to the 1/3. Now the probability that X is less than C is just the integral from 0 to C of the density, which is 1/2, because it's uniform from 0 to 2. Antiderivative, plug in limits, you get C over 2. Number 37, let the expected value of Y given X equal to 2X, the variance of Y given X equal to 4X squared, and let X have a uniform distribution on the interval 0 to 1. What is the variance of Y? Now, 37 is an interesting problem. So we want to find the variance of Y, and we're given that X is uniform 0, 1. So that means the expected value of X is 1/2. And if you take the expected value of X squared, it means you plug in, X squared here times the density, which is 1, integrated over all possible values, you get 1/3. So the variance is expected value of X squared minus the mean squared, which you get 1/12. Okay, we'll use these two pieces of information later. Now here, I'm going to derive a formula, but on test day, these are one of those things you need to commit to memory for the test, because going through this is just time you don't need to spend. Okay, so the definition, or there's a formula for the variance of Y, which is expected value of Y squared minus the mean squared. And that's actually how we calculated the variance here. Now we're going to use this over and over and over. 2 or 3 times, you'll see. And then now we trick each of these. So the conditional expectation of, the expectation of this conditional expectation, you just get what's back in there. So this is equal to the expected Y of Y squared. So now we look at this piece. Now the squared's on the outside, and if we take the expected value of this conditional expectation, we just get the expected value of Y. So this is the same as this. Now, this is the part that we're going to use over and over. And if you only look at this piece for a second, the expected value of y squared is equal to the variance of y. Now you take that over and it's plus the square root of the mean. Okay, but this is a squared like this one. So we're going to replace this. Okay, this just comes down. So it's the variance of y given x plus the expected value of y given x quantity squared. So this is replaced by this. So it's, oh darn it. So these two are equal. Now we're going to take this expectation in, so you get the expected value of this, and then the expected value of this is this. We bring this down. But notice this is the expected value of something squared minus, the same thing, quantity squared. So this is like a variance. So this is the variance, so this comes down, this is the variance of the expected value of y given x. Okay, so this is the formula that you should commit to memory on the test. Now we plug in the values. It's given that this is 4 to the x squared, it's given that this is 2x, and then the expected value is this, and the variance, you pull out the 2, it comes a 4. Those numbers we derived earlier, and it's 4/3 and 1/3. The answer is 5/3. Number 38, let x be a continuous random variable with density f of x equal to 2e minus 2x, and let y equal e to the minus x. What is the density function g of y where non-zero? Number 38, we're asked to find the the density of g of y. And we're going to do it a couple different ways. The first is we're going to let y equal e to the x as in the problem. And we solve for x, which x is equal to minus log y. And the derivative, dx dy, is minus 1 over y. Now, just the transformation, f of, and then you plug in this x, here, into the density of x, times the absolute value of the Jacobian, which this then becomes this. That's the Jacobian, absolute value. The minuses cancel, the 2 comes up to the y, the e and the log cancel, we get 2y is the density. So the second approach is using a CDF, or the cumulative distribution approach. So g of y, which is the probability that y is less than or equal to y, and substituting in y here, you get this, and then solving for x, you get the probability that x is greater than or equal to minus log y, and well, then that becomes the integral from minus log y to infinity of our density of x. Antiderivative, limits of integration, plug it in, you get y squared. So the density becomes, or the density f of y, or actually it's g of y, darn it, is the derivative of the CDF, which then derivative of this becomes 2y, and that's the same answer. Number 39, let x1 through x6 be a random sample from a distribution with density function f of x, which is theta e to the theta minus 1, x between 0 and 1, where theta is greater than 0. The null hypothesis that theta is equal to 1 is to be rejected in favor of the alternative that theta is greater than 1 if and only if at least 5 of the sample observations are larger than 0.7. What is the significance level of this test? So number 3, problem 39. Here We want to find the probability that at least 5 in our sample is greater than 0.7. So let's look that what's probably that one of them is greater than 0.7. And since these are uniform distributions, so what's the probability that one is greater than 0.7 under the null hypothesis? And then so you plug in theta equal to 1 in everywhere, and you just get a 1 here. And so the probability would be 0.7 to 1. Antiderivative, plug in the limits, that's 0.3. So this is probably that 1 in our sample is 0.7. So then we want to, so if we take a random sample of 6, and what's probably that at least 5 is greater than 0.7, so that becomes a binomial because each one is independent, and the probability that any one of those is greater than 0.7 is 0.3. So then this probability becomes the sum from I equals 5 to 6 of this. It becomes a binomial probability. And then writing this out, we get this and this. Factoring out a 0.3 to the 5th, and I do that because that's part of the answer, and you get this. Number 40, let x1, x2 be a random sample from a distribution with density function f of x equal to e to the minus x, x greater than 0. What is the density function of y equal to the minimum of x1 and x2 where non-zero? Now, number 40, we're going to solve it 2 different ways. First, we find the CDF of x. So cap f of x is from 0 to x of times our density, which is this. Take the antiderivative, plug in limits, we get this. Now we're going to use order statistics for this. And so y1 is the minimum. And this formula here, and it's not a general formula because it's not general right here, but this is something you're going to have to memorize on the test, how to find any order statistic. And once you learn how to do this, then it's very easy and very quick. So we're not going to derive that. So the density of the minimum of our sample of 2 is this. And then we plug in values. This evaluates to 2, f of x of y. Oh, darn it. So we should put in a y right there because that's a y. And then 1 minus cap f of x of y, which is this with the y plugged in. So that should be a y. And then this simplifies to this, where that's a y. And that's the answer. That's the density of f of y. So the second approach that we use is the cumulative CDF. So note that 1 minus cap f of y is a probability that y is greater than y. Cap y is greater than y. So, but y is the minimum of x1 and x2. So this is equivalent to both the x1 and x2 being greater than y. And then since x1 and x2 are independent, we get this. And that's the same distribution, or the density. So and note that being greater, probably we're greater than y, is actually 1 minus that. And so so 1 minus this, you're just left with the e, which is what we get here. And there's 2 of them, so it's the product, and we get e to the minus 2x. But that's 1 minus y. So we can solve for this, and it becomes cap f of y is this. But then to find the density, we have to take the derivative. So f of y is the derivative of this. which is 2e to the x. And again, since I use y, that should be y, this should be y, but it's the same as what we got here. And there's one note, that there's an error in the answers. None of the answers are that, but I did it two different ways. I originally did it the first way and didn't come up with the answer, so I'm like, what? So I did it the second way and came up with the same thing, so I'm concluding that there's an error in the answers. Oh, number 41. Let x1 through x10 be the values of a random sample from a normal distribution with unknown mean mu and unknown variance sigma squared greater than 0. And let x bar be the sample mean and let s squared be the sample variance. Which of the following is a 95% confidence interval for mu? Number 41 is which one is the correct confidence interval, and here it involves just finding what the t value is, t of 0.025, 9 degrees of freedom, 2.26. The answer is A. Number 42. A researcher wants to test the null hypothesis that theta is equal to 0 versus the alternative hypothesis that theta is equal to 1, where theta is a parameter of the population of interest. The statistic W, based on a random sample of the population, is used to test the hypothesis. Suppose that under the null hypothesis, W has a normal distribution with mean 0 and variance 1, and under the alternative hypothesis, W has a normal distribution with mean 4 and variance 1. If the null hypothesis is rejected when W is greater than 1.5, then what are the probabilities of a type 1 or type 2 error respectively? Number 42, we want to find the probability of a type 1 and type 2 error. So type 1 error is when the null hypothesis is true, so we're under the null, and we reject it and conclude that it's not true. So this, and it said that we need to be greater than 1.5. So it's when our test statistic is greater than 1.5, we're in the rejection region. We want to find that probability. So here, if we subtract the mean of 0 and divide by the standard deviation of 1, and then we get, because we know the mean and the variance, we don't, it's exact. So we subtract the mean, subtract the standard deviation, we get the same thing. You know, if you do it to one, you do it the other. So this is the same as probably Z is greater than 1.5. Look it up in a book, which is roughly this. Now to find the type 2 error, the probability of a type 2 error, we have to assume that the alternative is true, which means we're under H1, and we do not reject, so it means we're less than 1.5. But since the alternative is true, this is the distribution. It's assumed to be a mean of 4 and a variance of 1. So the probability that W is less than 1.5. So we subtract the mean of 4 to both sides, divide by the standard deviation of 1. So then this becomes a probability that Z is less than or equal to minus 2.5, which is, in my book, is this, which is pretty darn close to 0.01. So that's it. That's all I have for today. Hope you enjoyed it. If you did, please like the video, subscribe so you don't miss the next one. We have one more video for sample exam 7, and then we'll start in on sample exam 8. Thanks. Bye.